The fourth problem from last weekly contest, similar to the third problem, we are given two trees, tree 1 and tree 2, and we are asked to find the maximum possible number of target nodes for every node inside tree 1. But this time the target node definition is different. We don't have a K, but we have, uh, let's see the definition. We have this node U to node V. Node V is a target here if the number of edges on the paths from U to V is even. So that means if I connect this to this, then this is not a target node. This is a target node since this has 1, 2, right? This in itself is a target node because 0 is also considered even here. This is a target node, target node. This is not a target node. This is not a target node. This is a target node, target node, right? So all the even nodes or all the nodes that are at even distances is a target node. All right. In that case, let's look at it this way. If I would have connected it to this one, then it's just a flip of this particular possibility, right? All the nodes that are marked here will be unmarked and all the nodes that are not marked will be marked, right? Which means this will be marked, this will be marked. Sorry, this will not be marked, this will be marked, and this will be marked. Because now let's see if we are correct. This is at 2 distance, so we are good. 2 distance, we are good. 1, 2, 3, 4 distance, we are good. All the other ones which were marked earlier are now not marked. So we can see we don't have a lot of room to change things, right? Either these are the ones that we take or these are the ones that we take. So we can just recalculate this in two variables. We can just recalculate it in two variables. And a similar thing needs to be done here as well. So for this particular node, these are the ones that are not selected. These are the ones that are selected. So we see that we can mark every node if it is even or if it is odd, right? So if it is even, I can mark it, or if it is odd, I can mark it 0. If it is even, I can mark it 1. And similarly, I'll do the same thing here. I will have since we are marking bits 0 and 1, let's have a parity parity array 2 and parity 1. Sorry for the bad handwriting. And we will, for every node, mark 0 or 1 by the end of, this parity 2 population. We will go through parity 2, count the number of zeros, count the number of ones, take the maximum of the two, and use that as the contribution for this, for every node inside tree 1, right? Because one of them will be the contribution, I will take the maximum one as the contribution from tree 2. So we are done with tree 2. What about tree 1? Well, if I consider this particular node and it was marked with a parity of 1, then I will take all the others which has a parity of 1. So I'll keep a sum of zeros and ones, and for every node that I visit, I'll check if it's parity 1, then I'll take the total of 1 from parity 1. If I see that the node is marked 0, then I'll take the total of parity 0 and add whatever that we have decided for parity for the tree 2 as well. So it's pretty straightforward uh, in terms of coding. So let's jump into the code. Since we are going to construct the adjacency list for the two trees, so let's have edges 1 dot size plus 1, and let's have m is equal to edges 2 dot size plus 1. Let's construct the adjacency list, adj list. Let's have a vector of int, which is adjacency 1. Let's construct it. So construct function will return me the adjacency list, which will be constructed upon these edges 1 and edges 2 for list 2. So let's have the uh, function here, vector of int is what it is going to return. Construct is the name. It is going to take edges, so that will be passed by reference. I will create a adjacency list which I'm going to return. It will be of size edges plus size plus 1. For every edge in edges, I'm going to, since this is undirected, I will add it both ways. This will be edge 1. Let's copy paste this with the other way around and return the adjacency list or the ADJ. So now we have the adjacency list constructed. Next thing is what we need is the parity parity arrays. I don't know why I'm seeing errors. Parity tree 2, or let's call parity 2, which will be of size m minus m. Let's initialize this with values -1, and let's have parity 1 as well for tree 1. This is for tree 2, this is for tree 1. So I'm going to do a BFS, a simple BFS is going to populate parity 2. So let's do that. So not for every node, I'll do a BFS starting from 0th node. Since it is a valid tree, all of them will be connected, so we don't have to worry about that. So starting from this particular node, this is the starting node, we'll pass the adjacency list and we'll pass the parity that we need to fill. So parity tree 2 or parity 2, I'm sorry, needs to be populated. So it's not going to return anything, it's a void function. We are going to have a vector. So the start node, the adjacency list passed by reference, and the parity array. So inside the BFS function, we are going to have a queue initialized with the start node. So start node will be added. We don't really need the visited array here because we can use the parity array itself to see if it is -1, which means it is not visited. If it is not -1, it means it's visited. So the starting node will be updated. Suppose parity 0, which denotes even node, right? These are even nodes. Where we have 1, those are odd nodes. So let's have a bit which will be initially 1, which I'll flip and populate the parity bit accordingly. So while the queue is not empty, we will go level by level, and after every level we will flip the bit. So I'll have a size which is queue size. So while size is present, I will get the node from queue.front. Okay, I'm sorry. Pop it from queue, reduce the size for every neighbor node. Let's push it inside the queue if it is not visited, and every time we do that, so if it is not visited, that means parity of the neighbor node is not equal to -1 or equal to -1, which means it's not visited. Let's visit this by updating the parity to whatever bit value it is, and push it inside the queue. So after every level, let's flip the bit, and that is it. We're done with the BFS function. Alright, so now if we have, we have the parity arrays populated. So I'll do the same population for the first tree as well, for the first list. Alright, so now we need to calculate the max or the contribution from tree 2, which will be the max of the total even bits and the total odd bits. So let's call max tree 2, which will be nothing but a max of count of parity 2 dot begin, comma parity 2 dot end, comma 0th bit, and similarly a count of 1 bit. This is the contribution from max from tree 2 for every node in tree 1, right? So now let's populate uh, the answer inside this variable answer. So for every node which will be going from 0 till n, we'll check if the parity 1 of I is equal to 0, then we will take the contribution or the count of 0 plus tree 2 contribution, or let me call it tree 2 count. So answer will be, in that case, count of 0, total count of 0. So let's calculate that. Count even, which will be total count of 0, because we are considering 0 as even, and we are doing that on parity 1. Similarly, I'll do the same thing for odd as well, and that will be a count of ones. So here we are taking count of 0, so count even plus max tree 2, else we are taking count of 1, which is count of odd, and that's it. Returning the answer here. Let's see if this works. Of course it doesn't, because answer or pushback is is of different type. So vector of int is what we need. Okay, my bad. It should be auto. Let's see now. Parity of neighbor, which is a vector of int. Parity of neighbor, which means I am not initializing it correctly. This should be n. Let's see now. Okay, this works. This time the time complexity will be O of n, or it should be O of n plus m, and the space complexity will also be O of n plus m, because we are essentially building the adjacency list. So that's the fourth problem. Thanks.